This is Group 58, discussion or recitation 14.
All right, so this week's recitation was kind of different. I know it says angular momentum 3, but I feel like I had to use almost all the principles on this one in order to solve it. I think that's what they want you to do though, because it says use multiple fundamental principles to solve more complex problems. So this recitation was really tough, but I think I did at least as much as I could and came to some decent conclusions. But problem one, you got this diagram here. So you have a cylinder of mass M, radius R, on an inclined plane, and then it has a thin belt wrapped around it, and you exert a force F on the belt by pulling its end up the plane as shown. And then you're supposed to determine various things about this cylinder string ramp system. So part one, it says determine the magnitude of force you must exert on the belt to hold the cylinder at rest on the incline. Does also determine the magnitudes and directions of all other forces exerted on the cylinder by objects in its surroundings. So the forces we're going to have is going to be a normal force, a friction force. You're obviously going to have the force of this string and then the force of gravity. So that's going to be the four forces acting on it. And so you can see that the net force is going to be equal to 0 because we know the momentum of this object is not changing over time. We're holding it at rest. So looking at it in the x direction, we could say that the friction of x minus mg sine theta plus the force of this belt is equal to 0. And looking at the y direction, the normal force minus mg cosine theta is also equal to 0. But this tells us that the normal force is also equal to mg cosine theta. Then if we look at it from a angular momentum point of view, we also know that the angular momentum is not changing. So the net torque has to be equal to 0. And the only things applying torque in this case would be the friction force and the belt. So we know that the friction force is equal to the force of the belt. Plug that in to this first equation. You can see that 2 times the force you're holding is equal to mg sine theta. So the force of the belt is mg sine theta over 2 in order to hold the ball at rest. Is that what you guys got?
Yep.
Yeah.
Sounds about right.
Cool. So for part 2, it says that the cylinder is still at rest on the inclined plane, but now you begin to pull the belt up the plane with a constant force magnitude F, or constant force magnitude F that is twice the force you exerted to hold the cylinder in place. It says the larger force causes the cylinder to roll up the incline, obviously, without slipping. And then it asks, what is the cylinder speed when it has moved a distance d up the incline? So obviously, when we're talking about a force times the distance, I automatically think work, right? So I use the energy principle to solve this. And so you can see that the change in energy of the system is equal to the work done by the surroundings, which is the work from the pulling force that we do, plus the work done by gravity. So you have 2 times the force of the belt because it says it's twice this force, minus mg d sine theta. And so if you just break it down, we know that this change in kinetic energy plus the change in, what is that, like linear kinetic energy and rotational kinetic energy, so like k transit and k relative, is going to be equal to 2 times f d minus mg d sine theta. And so just going down the line, you guys can kind of see my reasoning. So like in this step, I just converted omega into v, and then it changes the fraction. And then it's pretty much algebra from here. But when you get to the end, take the square root of this, and you see that velocity after it's moved a distance d up the incline is equal to 2 root gd sine theta over 3. Is that what you guys got?
Yep.
Yep.
And then asking about the friction force exerted on the inclined plane. So I just set this one equal to the delta K trans, which we know would be F net times D. And so we just have the force of D minus mgd sine theta plus the force of friction times D. In this case, FD and MGD sine theta are going to cancel each other out because this time this force is twice what it was up here. And so we know that delta K trans is equal to the friction force times the distance. So you can just solve and say that the friction force is 2/3 mg sine theta.
Yep.
Is that what you guys got?
Yep.
I think so.
Okay. And then this problem was absolutely insane. I don't even know if I got to the right conclusion. I probably messed up my numbers or something somewhere. But this time it's asking us to pull on the belt so that it remains at rest until a time t when we abruptly cut the magnitude of F, not completely, but only in half. And as a result, the cylinder rolls down the incline without slipping, and it asks us to find the speed at a later time t final. So to start off, I knew I was going to need like multiple equations to solve variables. So I have that the change in momentum is equal to F net delta T, which in this case, since the mass is not changing, we could just say it's M delta V F net delta T. So solve for delta D or delta V. So plug in all the forces, do some algebra and factor things out, and you get this big ugly equation. But previous to the last question, we also know that the angular momentum is going to change. So we could say delta L is equal to the net torque times delta T. So we have I omega, but in this case, obviously I is not changing. So it's just going to be determined by the change in omega. And then you set it equal to the torque, which is the R times friction minus R times F delta T. And then same as last time, you divide out the R, you can solve this in terms of V. So I solved this one in terms of V. So now we have two expressions for delta V. If you do a lot of algebra and a lot of head scratching and hair pulling, you eventually come to the conclusion that the change in velocity from T initial to T final, is, what in the world is going on? Hold on. Retransmission is negative 1/3 G sine theta times T final minus T initial. Did you guys get that?
I think that's what I got.
Yeah, I think so.
That
That-
looks similar. I don't remember.
I don't
exactly.
know. This problem was like insanely hard, so I mean it's very possible that I mix it up, but if you guys think you got that, then I'll just leave it for now. And then problem 2 was like really easy, honestly, compared to 1. Pretty sure we had a problem like this in our homework. It's just this apparatus with the 4-point masses attached to it. We've seen this thing a million times this year. Nobody's new to this. And so basically it just defines all the masses and the length of everything. Then it tells us that we apply a force of 21 newtons per 0.2 seconds and asks us for the angular speed. So like before, you just say that the change in angular momentum is equal to torque net delta T. So you could just say that I delta omega is equal to the torque net delta T. If you solve for I in this case, it's 1/2 mr squared plus 4mb squared times delta omega. And then the net torque would just be the force times the radius times delta T. Solve for omega, solve for delta omega, which is also the omega final because it's initially at rest. And you get 11.96 rads per second. Did you guys get that?
Yeah, I just rounded it up to 12, but yeah, got exactly the same.
Yeah, so same thing. But yeah, that was all there was for this week's recitation. So if you guys
So,
have anything else to ask, go ahead and do it now. But I feel like this is pretty good.
Yep. Yeah, that's not recording.